Okay, let's go ahead and get started, even as people are starting to come in. So as always, welcome everybody to our bi-weekly observatory Zooms and science updates. I'm Karen O'Neill. I'm the director here at Green Bank Observatory. So today I'll give you, as always, a quick overview of some of the stuff going on here at Green Bank. And then from there, we'll pop right onto the highlight, which will be a talk about ion neutral connection and dense cores. So let me start off, as always, with a little bit about what's going on here at the observatory. Of course, as always, a little bit about COVID as well. So within the state of West Virginia, within the county, the number of vaccinated people continues to rise, but not very quickly at all anymore. So it's going up at an extremely slow rate, which is too bad. However, we are also seeing, as is happening around much of the US and much of Europe as well, we're starting to see the number of COVID cases rising. Again, this is due to both the influx of the Delta variant as well as the number of vaccinated folks is not going up at the same rate. So that's unfortunate, but we're hopeful that we'll start to see an increase in vaccines and see the number of cases begin to decrease again. On site, as I've mentioned before, we're seeing a return to work. That's very exciting for us. More and more staff are showing up as they come in from as readjusting from the last year and a bunch of months of working from home. So we've still got our health checks in place, but we anticipate full operations on site resuming on September the 1st. At that point, all of our staff will be on site. And it's been great to start seeing faces again and even seeing faces without masks so we can remember what everybody's mouths and nose look like. So that's been very nice. Of course, we're in the middle of the summer, so that means it's summer maintenance. This is an inspection year for us. So we've got inspectors crawling all over the telescope, taking a look at it, and our usual painting going on, actuator repairs, track work, things like that. All of that's been happening. Our Science Center has reopened to the general public. This is very, very exciting for us. So it's been really great seeing people again. We're able to restart our bus tours. All of this does require tickets. This is so that we can limit the number of people in the area. And of course, it requires masks, as we don't know everybody's vaccinated status. Everybody in the Science Center, everybody on the tours is masked. But it's been really great to see that. And we are working right now with our safety division to try to increase the number of tours that we have and increase the number of tours we can have in the Science Center. So that's been great. Other news on site, of course, our summer student program is well underway. This is a combination of 3 types of programs. It's the NSF-funded Research Experience for Undergraduates program that we share with the National Radio Astronomy Observatory. We also have a program known as PING, which is Physics Inspiring the Next Generation. And then we have a number of internships funneled in from various organizations here on site. So all the different students there. The program is currently remote, and the picture you can see here is not just Green Bank Observatory summer students, but also some of NRAO's summer students. But all of our, excitingly, all of our vaccinated summer students for both Green Bank and the NRAO will be gathering here in Green Bank in just 2 weeks and get to see them face to face, which is fun, and they'll get to tour the telescope and actually get to meet each other through a non-electronic interface. So that's all coming up. And this will be the biggest group that we've had on site since the pandemic started, which is also quite exciting for us. Other things going on around the observatory, hopefully all of you know this, but the GVT call for proposals for the 22A semester is open. The submission deadline is on Monday, August the 2nd at 5 p.m. Eastern Daylight Time, 2100 UTC. You can see lots of web links here if you're interested, but the main thing to do is to go to our webpage and you can find out about the call for proposal. You can ask for help if you need help with the proposal and things like that. Other things going on, we've got a lot of job openings. A lot of jobs were put on hold hirings were put on hold during the pandemic. So we're excited to see these openings and excited to see all of you pass the word out about these positions that are out there. We're starting to go through the great applications we have and look for them. Again, all of these applications are online. You can go just through our website, and under the About page, you can see careers where there's a link to every job opening we have. And that link will actually take you to all the job opening from all the AUI facilities. So any AUI job is posted on that career site if you're interested in the other jobs as well. Of course, we're continuing our community Zooms. We love talking to you guys. We love the chance to tell you guys about everything that's going on with the observatory. So our next one will be on July 20. That's today. That's interesting. I must have my dates off. So you can see the next couple of talks coming up on there, and I apologize for having things off a little bit on the dates. And then the last couple of things going off are with the proposal deadline, we're trying something new. We're going to have a couple proposal planning workshops coming up. These are both completely virtual half-day workshops on July 22nd and 27th. And so I encourage you to go online. If you're thinking about proposing to use the GBT, you can see a full schedule on there. You can call into the entire thing or just part of that, part of those workshops if you'd like. And then we've got our single dish school, which is also tied this round this fall to the observer training workshop. So both of those are back to back. Those are coming up at the end of September. The single dish school and observer training will be hybrid. So it'll be both in-person and remote options out there. And signups for both of those you can find through our main webpage, or you can go through these links if you want to find them. You can find both of that information on those. So with that, I will hand this off to Jay to introduce today's speaker.
Thanks very much. Today's speaker is Jaime Pineda from the Max-Planck-Institut for Extraterrestrial Physics, and he's going to be talking about the ion-neutral connection in molecular clouds. And if you have questions, please use the Q&A button in the lower right of your screen, and I will be handling those and passing those on to Jaime.
Awesome. Thank you, Jay, for the introduction. And thank you all for the opportunity to show some of the results that are really enabled thanks to the instrumentation available at the GBT. So I will talk about the ion neutral connection in dense cores. And I'm going to show here the fantastic team that helped me through the project, involving people here at the Max Planck, but also the fantastic team at the Argus team getting the instrument ready. So the main point that I would like to focus is on star formation. So in terms of star formation, if you take a look at the full cycle that we think that the system is gonna go through, is we start with a large cloud of usually observing CO. And then at some point it starts to fragment and accumulate into even smaller and denser objects called dense cores. And it's in these objects where we think that star formation is going to provide usually a single system. In these systems is where when we go further in time, we can form a protoplanetary disk and further have a planet formation. So some of the important aspects of the whole process, going from a large molecular cloud into cores and into planets, is the formation of the individual steps and how do we transition from the different steps. And for that, some of the most important parameters is both turbulence and magnetic field. So turbulence, it's important because the molecular clouds that we observe are highly supersonic. These are molecular clouds with line widths that are much larger than the sound speed, meaning that they usually could provide enough energy to create shocks within these objects, but also this turbulence is usually expected to be driven by MHD waves. So we have alpha waves that are going to trigger or transfer the energy from different scales. And the magnetic field is extremely important, especially when we take a look at the formation of the disks, because the disk and the disk and star formation process is highly regulated by the interplay between the amount of turbulence and magnetic field. If we have a large amount of magnetic field, we can end up with an extremely small disk surrounding a star. So getting this constraint very well understood, it's very important to have a full picture of the star formation process. So if we start from this place, then we can think about what's the standard picture for the role of magnetic field. If we just take a look at one of these single units that are going to provide a star formation unit, then we have a dense core. And the mental picture we usually have is these are threaded by magnetic fields. And the standard picture, again, is we have magnetic field that is basically aligned. And then once this starts to collapse, when gravity starts to take over the other terms in the dynamics of the dense core, then we have this collapse, and it's going to bring the magnetic field lines inwards. So this is going to start to bend it. And that bending is due to the good coupling between ions and magnetic field. In the same way as we have this bending of the magnetic fields due to the dragging of due to the ions, we know that the neutrals, they don't know anything about the magnetic field, and therefore they should move faster. They should just collapse due to gravity. And the only information about the magnetic field can be transmitted through the collisions between ions and neutrals. Therefore, we think that ions, if they're tracing the same volume, they should present narrower line widths. And this is basically the standard ambipolar diffusion process in terms of how do you diffuse this magnetic field into the central region. On the other hand, turbulence has a very simple picture where we start from, in this plot, it shows the scale of in the y-axis, the amount of energy at a given scale in that eddy, in that scale of the turbulence, and the y-axis and the x-axis here, it shows you which scale are we talking about. So in this case, large scales are at the left, and small scales are at the right-hand side. So if we try to connect with observations, molecular clouds, big objects, they should be in this range, very large line widths, a lot of energy. If we go to smaller and smaller scale, then this turbulence is being transmitted, and it's injected to smaller scales, and then we see smaller and smaller line widths as we go into the smaller region. So we see that there is actually less energy present at smaller scales. And therefore, that implies that higher density tracers, if they're actually tracing smaller volumes, they should present narrower line widths. And this is well known. This is something that we observe in different tracers, and we see that it's a well-known fact that the line widths of larger scales are much broader than what we observe at smaller scales. So that's important. So one thing that we need to understand also is, if we want to know the role of the magnetic fields in the interaction with the turbulence, we need to try to study ions and neutrals to see what's the real effect. So one simple picture that we can think of is if we have this cascade of the turbulence going from large scales, so here at the bottom, large scale, down to small scales to the right. If we just take a look at the neutrals shown in light blue and the ions shown in red, we would see something slightly different. So when we look at large scales, the coupling between ions and neutrals is very good. And in this case, we see that they should have the same amount of energy, the same amount of turbulence. However, there is a point at which we start to see this difference between ions and neutrals. And at some scale, ions, they move less than neutrals. So this is the idea that if we are able to measure or estimate the difference between neutrals and ions at different scales, then we could estimate what is the actual ambipolar diffusion scale and what's the actual role on that formation. So the test is observe one of these dense cores with a nice ion-neutral pair at the sufficient sensitivity and angular resolution to this comparison. For this, we're going to be using targets that we've been studying in the past few years. It's called Barnard 5. The nice thing about this object is that when we observe this dense core with the GBT in ammonia, we were able to see the velocity dispersion not only in the core, shown here in this with this orange contour. The line widths inside are very subsonic, almost constant. And right outside the core, we have this turbulent medium, that's the turbulent cloud surrounding it. So this is an object that has such a beautiful transition that we are able to study at even higher angular resolution with the VLA combined with the GBT. and then we can see that there is further substructure within. So in this case, within the core, we see that there is 2 filaments, and there is evidence for a fragmentation into the northern block. We can do a further analysis on the structure within this subsonic region, but this is enough to have a really nice map. This is a beautiful, beautiful high sensitivity, high angular resolution map of neutrals. Ammonia is a really good dense gas tracer, and it's a neutral. So now we need the ion. We need a pair, an ion pair that's going to allow us to do the same comparison. For that is when we need to go to the GBT. So the observations that we obtain with the GBT are shown here on the left panel in blue. So usually in this plot, we're going to be showing ions in blue and neutrals in red. The ions here shown by the N2H+, we can see that the map is very large, actually covers a large enough region that we can actually cover the whole dense core. And if we compare with the neutral here in the middle panel, ammonia 1,1, we can see that actually they trace more or less the same structures. Therefore, they're likely to trace the same volume. So we have a pair of lines that now we know are tracing more or less the same volume on the space. So now we would like to know what happens with the velocity dispersion. Now we can try to do this comparison and see if there is a variation of the line width in ions and neutrals. So we go here and we make a velocity dispersion map for both tracers. So in this case, we have again the ion on the left and the neutral on the right. The markers here, the circles and the star are shown in both sides, so you can have an anchoring point to see how similar or different the maps look like. They are shown also at the same scale, and the velocities are obtained in this case thanks to the hyperfine structure of both lines. Both lines, they have a beautiful hyperfine structure that is well known, well constrained, and allow us to have a really good constraint on the line width center velocities at each pixel. So in this case, we have these maps that more or less they look similar. However, I need to point out that actually the one on the left, it looks a little bit lighter in color. When it looks a bit lighter in color, it means that the line width is a bit broader. So this already shows us that maybe the ions are doing something different. When we take a look at the ratio map, we can see something very surprising. So this is the ratio of the line width between neutral and ion, meaning that if the line widths of the neutrals are smaller, it will look red. You can see that overall this map looks mostly red. The only places where we can see blue colors are mostly at the edges, and that's because at the edges we have sufficient sensitivity in the ammonia map to start to pick up this transition to coherence, so the transition between the subsonic core and the turbulent clouds surrounding it. That means that in this case, ammonia could be tracing even larger scales than N2H+. So in this case, if we just do this simple comparison, we already see something interesting. Now, what we're going to do is we're going to estimate what's the amount of turbulence that we trace at each pixel for each object, for each tracer, ion and neutral, because we have a very good estimate of the temperature, thanks to also the fact that we can observe ammonia 1,1 and 2,2 at the same time. The ratio of both lines of the ammonia 1,1 and 2,2 give us a good determination of the kinetic temperature. So we can use that as the estimate for the sound speed also. So in this case, we make a plot of the sonic Mach number for both tracers. Here in the left plot, we have a distribution, the distribution of line width or of Mach number obtained with each tracer. You can see that ammonia, the neutral, that is supposed to be tracing the slightly larger scale than N2H+, has narrower line width. this was surprising. The line widths are about 20% higher in the ions. If we do a one-to-one comparison of every single pixel, we actually see that's what we see in the right-hand side. We see that for almost every pixel, they're shifted. These black lines show us the one-to-one correlation between the turbulence traced by N2H+ and ammonia. So this is something that we're measuring, and it's throughout the map, and it's systematically. We're seeing that the line widths of ions are broader than neutrons. So this is absolutely inconsistent with our standard picture. So how do we interpret this? So we have that the ion, which is also a higher density tracer, shows a broader line width than the neutral counterpart, which is a slightly lower density tracer. So this is something like an inverse ambipolar diffusion. The interpretation that we have is that actually now we have very nice evidence for penetration of MHD waves inside the core. So if we go back to the standard picture of magnetic fields threading the dense core here in the middle, now we think that there is an MHD wave that is getting to the core. And the MHD wave is such that it transmits inside and it perturbs the B field. The magnetic field is perturbed. Now the perturbation in the magnetic field affects mostly the ions. So we're steering the ions much more than the neutrals are affected. And that discrepancy is seen in the line width. That's why the ions are broader than the neutrons. So we can estimate the perturbation in the magnetic field, and we estimate that this perturbation is quite large. It's 27 microgauss. This is at minimum 5% of what expect the upper limits that we have. It could be much, much higher depending on what's the actual magnetic field strength that we see. In this case, just since we're running out and getting to the end of the talk, we have the results of it is the first time we're resolving ions and neutrals in such a way that we can see the neutrals having a narrower line width throughout the map. The magnetic field also inside the dense core, maybe it's not static. Maybe now we need to think or rethink our models of MHD inside cores and say that actually the magnetic fields are not static. And also thankfully to the use of the GBT, this was done with excellent image fidelity, which was crucial to actually have an accurate determination of both the line profiles and the extent of the emission. We need to keep looking for this and see if there are other pairs of ion neutral lines that can allow us to prove how deep is the wave penetration. What happens with this wave penetration at much higher densities? Is this enough to perturb the magnetic field sufficiently that it can, for example, misalign the magnetic field and the rotation of disks, for example? That would be really surprising. So I think this opens up a new window to study magnetic fields within dense cores that we had not before. Thank you.
Thank you very much for a most excellent and provocative presentation. Questions should be delivered through the Q&A window on your lower right, and we have one already. Do you have the polarization maps for this source? What does it look like?
That's a great question, and that's one that we've been proposing for a couple of years to different telescopes. Unfortunately, either polarization maps of this source have not been obtained. For example, with SOFIA, they're not sensitive enough to get the polarization maps of this core. Or in the case of JCMT, we got the proposal accepted. We were in the queue, but unfortunately, it didn't get observed. We're hoping that in the near future, instruments like, for example, NICA-2, the polarimeter in NICA-2 can get commissioned soon. So then we can actually have such a measurement, because that's key. So if we're able to get an estimate of the magnetic field, the orientation of that, if we see variation, of the orientations at these scales, then we can try to link.
Okay, we have another question. Can you then put a minimum value on the static magnetic field strength in the core, and therefore the magnetic virial term?
So in the case of this object, what we've been able to do is in a previous paper by Annika Schmiedeke, we were able to estimate the amount of magnetic field required to support the filaments that we resolve. In this case, we obtain upper limits on the magnetic field strength of about 500 microgauss. That is a wildly high upper limit, but it is because the filaments are quite dense. We don't have an estimate of the magnetic field in the less dense regions of the core, unfortunately.
Okay, another question. Could this trend depend on the mass of the cores? Could more massive cores be more influenced? And do you have an idea of how this trend evolves with time as collapse proceeds?
That's an interesting question. We have not really explored what happens as a function of time for two reasons. These waves, they're dissipating very fast. They should be dissipated in less than the crossing time of the core, meaning that probably we're getting this core affected the whole time by MHD waves. And that's one way to keep pumping the amount of turbulence within the core, and maybe that's one way to really very efficiently dissipate the amount of turbulence in the cloud. But in this case, also the fact that this would be a density effect is important, because if we look at the let me see here. So the next slide. Let me see. The variation in the magnetic field depends on which density we're actually observing. So this is something that it could be highly dependent on density, but it should depend a lot on what's the MHD wave that's impinging the core, and what's the ion neutral interaction. So it depends on the ionization fraction in a way.
I think if you go back to the previous slide, that'll be relevant to the next question, which is, your plots of the line width seem to show that the ions had 2 peaks and the neutrals 1, with one of the ion peaks agreeing with the neutrals and the other at a lower value. Actually, I think it's the reverse, isn't it? This seemed to suggest 2 ion components rather than a simple difference.
Yeah. So I think that's much nicely seen in this interratio map. So if we just take a look at the ratio map, this is basically what we're trying to understand is that most of the blue points, most of the objects at high at places where the neutrals are broader are right at the edge. So that's absolutely true. There are two populations. One is basically the core, and the other is the edge of the core that we're actually observing, and that's this very narrow skin surrounding the core, and that's what we think is the transition to the coherent cloud that we're seeing, to the turbulent cloud that we see, and that is not traced by N2H+, and that's the reason for that discrepancy.
And here's a question. Can the denser gas traced by N2H+ be perturbed more by an internal source, such as outflows from embedded protostars? In this case, the velocity dispersion difference might be explained by regions of different densities perturbed at different levels, rather than by ambipolar diffusion.
That is a really good point. And in this case, you can actually see that around, in this region, there is only one protostar. So that's the first point. Even though it is a large enough region in scales and in mass, there's more than 40 solar masses in this region of dense gas. However, there is only one protostar. This protostar at the center here. And you can see that actually the outflow that goes from this region, it goes in this direction. And the effect on the line width, you can see that around the protostar, the line widths are broader. They are significantly broader. But the rest of the cloud is really far, far from the outflow. So it is not a local effect. It's not an effect of the protostar. It's not an effect of the mechanical interaction of the outflow with the cloud. However, if the outflow themselves are affecting the MHD waves or the magnetic field at a scale larger than the core, then that could also affect the level of turbulence.
And finally, we're almost done with the questions, and there are two that can be combined into one, I think, and that is whether there are other dark cloud objects available for observation, and how about isotopic species of NH2 plus or NH3 in deuterium or nitrogen-15?
So let me start with different species. So in terms of isotopic ratios, we have not done the estimate of the rarer isotopic ratios. We do have data without sufficient spectral resolution, but sufficient enough to identify places with high levels of deuteration, and we see that the high levels of deuterations are along the filaments and picking up on the condensations on these objects that we see here. So that's one of the goals of some proposals that we have worked on, is can we see this effect at higher densities, and maybe with some of these ion neutral pairs that are using the deuterated partners. And so instead of ammonia, single deuterated ammonia, and instead of N2H plus and 2D plus, that is one of the things we're planning. And in terms of, so the question was about the objects? No. What was the other question, Jay?
Yeah, but well, actually, that was kind of superseded by another question that's come in. The Barnard 1 core was observed by the Bistro survey using JCMT. Have you observed the Barnard 1 core using this method? They found a plane of sky magnetic field strength of order 120 microgauss.
No, we have not. That is really a good question, because once we have been able to do this robust analysis, then that's the next point. The next project is, can we get this into more places? And actually, Barnard 1 is one of the places we would like to do the analysis. However, for that we need both. We need to obtain the ammonia and the N2H plus maps, and those are also going to be very large in time requirements. So we'll need to really determine what's the actual size we need to cover, because Barnard 1 has a very active region, and then there is a nice long cometary tail that it could be perfect for this kind of analysis.
Well, thank you very much. We've come to the end of our time and the end of open questions. I'd just like to remind everyone that this presentation will be uploaded and you can see it in a few days. Just go to the GBO website for instructions about how to connect with it. 2 weeks from now, please join us when we'll be hearing about GBT observations of green pea galaxies. And until then, thank you very much and goodbye.